So this video will get into Kelvin Planck's statement, which describe one aspect of second law of thermodynamics. We mentioned about in the previous video, second law of thermo is very abstract. The way I'm looking at is the way the direction goes. So the heat, for example, heat transfer from hot to cold. But there are many other aspects we're going to look into. So first, we're going to look at Kelvin Planck's statement. Before we look at Kelvin's Planck's statement, we're going to understand about thermal reservoir. So thermal reservoir is a system that remains constant temperature, even though there's energy added or removed by heat transfer. And for example, normally it's like a large body of mass, like Earth's atmosphere, right? And the lakes and the oceans and large blocks of solid. And for thermal reservoir is divided by two. One is called a source, another one is called a sink. So source is that something supply the energy and giving out the heat, and the sink is something receive it, absorb it. That's going to be the sink. We heard about heat sink all the time, right? It's trying to get for example, the heat sink for CPU is trying to get suck out the heat to keep the CPU cool. So what is Kelvin Planck's statement? I'm going to read this out and you're going to find it very abstract, and that's totally normal because soon we're going to break it down to a level that we can understand. It is said it's impossible for any system to operate a thermodynamic cycle and deliver a net amount of energy by work to its surrounding while only receiving energy by heat transfer from single reservoir. So you see big X. So that's a no. What do they mean? Not only receive heat transfer from one single reservoir, that's saying there's going to be another one right here going through the cold reservoir. Okay. Again, I know it's very abstract. So now let's look at it. First, I want to invite you to draw a heat engine. Okay. So we're going to use a heat engine as an example. Here we'll have our hot reservoir. Sometimes we also call TH, means at a higher temperature. Then going down, we have this thermodynamic circle. Inside we call heat engine, and it's a circle, so put our arrows in. And then we also have our cold reservoir. That's going to be at lower temperature, or we call TL, T-low. Okay, so the heat engine is going to convert the thermal energy to work out. That's heat engine. Okay. So heat engine is convert heat to work energy. But what's inside this heat engine, right? What's inside here? Now we're about to draw. This is like a quick preview of what a power plant looks like. So what's in here? We start with a pump. So that's a pump. So this is going to be low pressure. And after pump, it's going to come up with high pressure. If we consider this is going to be purified water, right? Pump up at high pressure. Then for pump, we learned we need have required energy working to increase the pressure to the low, from low to high. And after this, at high pressure, this water going to go through boiler. All it does is you add heat to it trying to increase this liquid form of water becomes superheated vapor. And this continues stay at high pressure, right? So during boiler process, the heat is added to boil or change from liquid to superheated. And we understand before, when pressure increases, our saturated temperature or our boiling temperature increases. And that is the purpose of this pump. Because when you pump it, you increase the pressure, and that allows you this temperature right here at boiler increases at higher temperature, right? Saturated temperature increases. Okay. Now, after coming through out the boiler, while going through this turbine, we know what turbine does is convert this thermal energy of superheated vapor to mechanical energy output. So basically this shaft is turning, or we call work out. Then what happened to going through the turbine? This become no pressure, right? When it's going down no pressure, and it's going to continue going through the fourth component, we call it condenser. Condense is a process changing from gas to liquid, right? That's condense. So what condenser does here is, if there were some mixture, if there's some gas form coming out of turbine, it's going to be completely changed to liquid at this no pressure. And then this process starts again. This no pressure liquid water is going to go through the pump and gets to the high pressure, and at this high pressure we'll be able to get higher saturated temperature during this heat added process in boiler. And you get this superheated vapor, and we have this strong thermal energy. We're going to convert that to mechanical energy to turn the shaft, because this shaft is actually upstream of generator. This shaft is going to turn inside the magnetic coil, and then that's how generation of electricity happens. And then when we have this water coming out of the turbine at low pressure, and if there's any gas form, it's going to be completely condensed to liquid. So this is going to be the whole process of heat engine. Okay, now there's a few things I need to add to it. For the condenser, when gas become liquid, we will lose the heat. So in that case, we will have heat coming out. So we'll have Q out. Okay. So notice at boiler we need to add a heat. For condenser we need to release the heat. For pump we need to require some work. For turbine we generate work. So that's work out. And so that's what's going on inside this heat engine right here, right? That's what's inside the heat engine. So where is our high temperature thermal reservoir that's going to be supplied the heat, right? That's going to be our boiler. And what will be our heat sink? This cold reservoir where all the heat is going to be absorbed. Heat leaving out, right? That's going to be where the condenser comes along. Okay, so knowing that, and then one more thing, what would be our workout? Our workout will be the shaft work coming out of the turbine. You might be curious about this working for the pump. you have two choices. Sometimes because this working is so negligible, it's very small. So in that situation, we don't even consider the working required to pump because that is way small compared to the turbine workout. And if sometimes situation, if it's not negligible, then we're just gonna use work shaft minus work required by the pump. Okay? So knowing and understand that concept, we can relate it to what we learned before about the efficiency. Because whenever we go to a power plant or any power plant, they always say generate electricity is not hard. We've done this for many, many years. However, what is difficult is increasing the efficiency. That's what engineers are trying to do. So efficiency, it is equals desired output over required input. Right? So for this situation, for our heat engine, what will be desired output? What do you want to have? So we call eta, that's going to be efficiency symbol. We add a subscript HE. Our desired output will be this workout. We want to crank out as much work as possible. That's workout. And what will be the absolutely required? We have to heat it up, right? So that's going to be our QA. Oops. Required heat. Okay? So that's going to be our first expression for heat engine. You want to get as much work out by the turbine, and you required the heat needed for boiler. Now let's hold this for a second. We're going to look at this entire circle, this thermodynamic circle, which is right here also, right? What is thermodynamic circle? If it's a circle, I'm sorry, did I say circle? Cycle, thermodynamic cycle. So if it's a cycle, which means initial and final points have to be coincided together. In that situation, our delta U, internal energy change, will be equal to 0 because the initial and end is the same, right? U2 minus U1, U2 equal to U1. Delta U equal to 0. We learned delta U equal to 0. First law, conservation of energy. Delta U is equal to heat transfer minus work. And so for this cycle, right here, we have heat coming in by the boiler, and we have heat leaking out at condenser. So we have Q in minus Q out. And the work, if we assume the working required by the pump is negligible, so we will only have work out, right? So in that situation, that equal to 0, what allow us to see is going to be Q in minus Q out is going to be equal to our workout. Okay, so that's our first law, conservation of energy for this heat engine cycle. One quick way you can thinking about it, instead of write down this equation, I felt it's easier for me just looking at this graph. For example, right here, this graph, we are going to add arrows now. So going back to this heat engine, so you have heat coming in through the boiler. And we're going to convert this heat to work energy, so you have workout. And however, inevitably, you have heat coming out of the system. Yeah, in other words, not all the heat coming from the boiler is going to convert it to workout. Inevitably, there will be some workout leaking out. That's actually this Kelvin Planck statement. Let's look at it again. It's impossible for any system to operate a cycle, deliver a net amount of work by its to surrounding while receiving only from a single reservoir, because you have to have some heat leaking out to the colder reservoir. That's Kelvin Planck. Okay, so knowing that, I told you I want to look at this thermodynamic cycle to come up this equation even quicker and more visually. It's looking at this graph here. Look at this cycle. What comes in? QA. What's left? The cycle, workout, and heat, right? Makes sense? All the heat come in, part of it going to the transfer to the workout energy, and part of it is leaking out. So in that case, you get the same equation in terms of how much workout you actually got. It's going to be Q in minus Q out, right? This is going to be same equation as you using over here. I like this latter version better. It's very visual to me. Okay, so knowing that, we can go back to our heat engine heat engine efficiency, because this equation can be further written in different way. So let's go ahead and wrap it up, this one. So heat engine is going to be equal to desired, which is workout, over required, heat required for the boiler. And this workout is also equal to heat coming from the hot reservoir minus heat leaking out to the cold reservoir divided by QA. To simplify that, we'll get 1 minus Q out over QA, right? So that's our heat engine efficiency. We have those two different formula. Okay. All right, so that's all for today for this particular video about Kelvin Planck statement. And hopefully by this time, it's not that abstract anymore. You understand using this heat engine as an example. And you know the heat cannot be completely 100% transferred to the workout. Inevitably, there will be some kind of heat leaking out to the cold reservoir. That's why I come up with thermal efficiency for heat engine. And then what's going on inside this cycle, right? In the graph, we see such an easy cycle, but what's in there? You have a lot involved. You have this pump and boiler and turbine and condenser. And wait until we actually go visit those power plant, you will see, oh my gosh, everything we saw in thermodynamics book is just a scheme, but you know, the components, however, it's very complicated and it's very highly advanced. But here, this is a basic bone of it. Understanding it will help us do things better. So this is the heat engine, and that's all. I'll see you next video. Bye.